We know so far from our study of line integrals that a line integral is a way to essentially compute a version of work. To what extent is something, some object, going with or against the flow of vectors in that vector field? So just to kind of rebuild this, because there are lots of pieces that sort of begin to come together, and so recognizing what it is that we're really doing is critical at this juncture. So I have some vector field, and I'm going to call that capital F, and it's going to depend upon two components, x and y. So this is in 2 dimensions. The analogy is the same in 3 dimensions. And let's just suppose that everywhere along this vector field, this vector is going to be the vector, we'll say, x0. Okay, so what that means that if I pick any point in this xy plane, for instance, at 0, 0, well, when x is 0, the x component of the vector is going to be 0, so we're going to get the vector 0, 0. In other words, a particle that starts at the origin will remain at the origin because it doesn't have any current associated with it. It has basically 0 magnitude current. Now if we move over one step, now this is equal to x0, so this will be a vector of length 1. I'm not going to go ahead and draw it necessarily of length 1, but it'll be a vector that points to the right. And at 2, 0, it'll be the vector 2, 0. So it'll be a longer vector. And as we move further and further away, these vectors get longer and longer. So we'll have kind of a short vector, a longer vector, longer vectors. And in the opposite direction, we'll have symmetry, since the values of x over here are just negative. Now, since the value of y actually doesn't affect the flow of where stuff is going, the y vectors up here will be exactly the same. They just get longer as x gets bigger. They get longer as x gets bigger. So we'll see something like this. So with the exception of anywhere where x is 0, if it starts along, a particle starts along the y-axis, that is where x is equal to 0, there will be no movement. Down here, same thing. The vector direction and size is only a function of again, the value of x itself. Okay, so we know that a particle that would be dropped somewhere within this stream, if you will. If I put a particle there, then I can pretty confidently say that this particle is going to go that way. And its y component shouldn't change because of the fact that the y component of each vector is 0, so the y component will not change. Now, what I want to do is, perhaps I have another path that I want to take, and it's not with the flow. Perhaps I want to start somewhere over here and maybe carve out a path like this. I'm going to row my boat gently down that stream. Now, since in some positions I'm going kind of with the current, like here, we have vectors everywhere. We're just drawing them spaced, otherwise putting in vectors at every single point would make this into a mess. And then even along here, the vectors are actually pointing to the right, but my flow is kind of against the grain. So what I'm going to see is that here I have a position vector. My position is along that green curve, and here I have a small angle relative to the current vector. Up here, my position vector is, again, tangent to my path, and so here we kind of see more of perhaps a 90 degree. So we have a 0 dot product between our trajectory and the vector field. And then over here, we see that the angle is now obtuse, and that means I'm kind of going against the current. My x component is against the direction of the x component of the water current itself, and even more so here. Now we've just kind of isolated 4 points. But at every one of these points, we have a position, which I'm going to write as R. And many times it's easier to parameterize this curve and write it in terms of a parameter t. So maybe your x is equal to 2t and your y is equal to cosine of t. That way, as t varies, x and y can change according to the functions that represent them. So I have some r of t function, and then I am going to dot that. That's going to be a dot product between the r of t vector and the f at that position, f of r of t. And that's going to give me the sort of the amount of work at any one of these stationary points. Now, of course, what I want to do is I am going to break this curve up into infinitesimally small intervals so that I basically have infinitely many points along here, because this is just going to give me these 4 dot products. If I sum those together, if I take circle 1 plus circle 2 plus circle 3 plus circle 4, these are not zeros, then I will get some number which will represent the extent to which I am going with or against the current. Of course, to be able to add up infinitely many of these, because this is going to give me an approximation of the work being done, the force times the distance, if you will. What I'd be better off doing is adding up infinitely many small vectors where this is going to be f of r, okay? This is some vector f, which is a function of the position that we're at, so a vector that depends on another vector, dotted with these infinitesimally small change in position vectors. So just imagine that these are teeny tiny vectors all the way along this green oriented curve. So this oriented curve is something we typically call C. So this is we'll call that C. And so we want to add up all those dot products along that curve. And since we parameterize most of the time anyway, this is going to be the integral of f of r of t. Right, so we just said that we're typically going to write x and y. These guys are both going to be written in terms of this parameter t, because again, it's just easier to do that oftentimes. And from what we've learned, we know that this is going to be the derivative of the position vector with respect to time dt. And this was our equivalent parameterized line integral. And this is again along that oriented curve C. That's just going to represent my time initial and my time final. So here we'll have t initial, and here we'll have our upper boundary will be the time final. So basically at time t0, we'll be at this point, and then we'll be moving along this curve, and then eventually at time final, we'll get to that point right there. All right. Now that we have a better sense of that, and by the way, we know that the dot product between two vectors that are less than 90 degrees, if that's theta right there, then the dot product between them, x dot y, well, will be positive. So I'll write that as greater than 0. Similarly, if the two vectors x and y are perpendicular, then the dot product will equal 0. This is a greater than sign. This dot product will equal 0. And finally, if the angle between x and y is larger than 90 degrees, then the dot product will be negative. Awesome. So this is just our little summary recap. So that means that if we sum up all of these dot products and we get something that turns out to be positive, well, that means even though in some instances we may have gone against the current, for the most part, we tended to go with the current. The current did more work on us than we did against the current. If the dot product is 0, well, that could happen if, for instance, you went exactly perpendicular, right? In that case, you're not doing work on the vector field, and the vector field isn't doing work on you. And notice how I said that. I didn't say that there isn't work happening. I just said that the position, the displacement, relative to the vector field, it neither inhibits nor is supported by that vector field. It does not, they're perpendicular, they're completely orthogonal. Versus if I get a negative dot product, that means predominantly I was going against the current. Okay, so now that we have this recap, this setup, we often have what are called path-independent fields. Now, what this means is that in some instances, like if this were to represent the ground, and I were to take an object up here, and I were to basically cause it to displace towards the ground, well, one way to do that would be to drop it. Another way would be for me to hold this object and kind of curve it back and forth, kind of like this, and then place it on the ground. Well, if the only force vector is the constant force of gravity, then notice that the amount of work in both cases is going to be the same. That is, gravity did the same amount of work on what we'll call C2 as it did on this path C1, right? Relative to that field, if you just think about it intuitively, gravity did the same amount of work on that object. Now, if that object were to go up and down, let's think about it this way. If I were to lift it up, or drop it down, lift it back up, drop it down, lift it back up, drop it down, believe it or not, that's going to require the same amount of gravitational work. How can that be if it has to come down multiple times? Well, think about this and this as sort of canceling each other out, right? Here, gravity is doing work, but then I'm doing work against gravity. So those nullify each other. And so C3 will have the same amount of work. So these are what would be called, this is one example of a path-independent field. That it didn't matter which path that ball took to get from this vertical position here down to the ground, it is going to require the same amount of work. It's going to be an identical amount of work. Well, this all comes back to the fundamental theorem of calculus. The fundamental theorem of calculus we've been using all along. It's allowed us to compute definite integrals. And the idea here behind the fundamental theorem, it basically stated that if you know you have some sort of rate of change function, for example, and maybe that rate of change is the speed of a car, that let's just say that simple example of you have the speed of a car, which we'll measure in miles per hour, as a function of time. Let's just say this is a constant f prime of t equals 50. So that means that the car is going 50 miles per hour. Well, if we sketched that position graph, versus time, then over time what we would have is something like this. In other words, the miles, or that is the position of the car, how far it's gone from where it started. Well, it started at, we'll just say at this, for this particular case, it started at a position of 0, and then every 1 hour, we know that this displacement here should be 50 miles. And at time 2 hours, the displacement would be 100 miles. So if I were to say that this is right here, time equals b, and this right here is time equals a, and I wanted to find the total distance that car had traveled, well, I'm going to take the position at time b, and it doesn't have to be at t equals 0. The t equals a could be somewhere right here, for example. And then I'll take that position, whatever it is, f of a, position at time a, and then take the difference, which will effectively give me this distance right here, that change in position. And that will be f of b minus f of a. So there's our kind of intuitive example of what this fundamental theorem of calculus tells us. It basically accumulates all of the area under this curve. Now, we have an analogy before we get into this idea of path independence. In vector calculus, f prime of t is the same as grad f, the gradient of f. Remember, there are two derivatives associated with a multivariable function that's in 3 dimensions. There's the derivative with respect to x and the derivative with respect to y. Now, we're just right now looking at f of x, y, z, but analogously, for 3 dimensions, we would just have fx, fy, and fz. And our endpoints are ordered pairs we are moving from and to. Let's say we move from a point P to a point Q. Okay, so we have some vector field, a gradient field, and maybe this gradient field looks like that. Just to kind of shake things up, we'll make them different lengths. And then we are moving from a point P here. P is just going to be some point, we'll call it x1, y1. And then we're moving maybe to a point Q that's over here. So there's our oriented curve. We're moving from point P to point Q. Q is just some other point x2, y2. Now, in this sense, in order to use the fundamental theorem, you need to know both the x and the y coordinate. And up here, that integral was from a to b. But now, if we replace the derivative in single variable calculus to the derivative analogy in multivariable calculus, that's going to be grad f. That's going to be a vector of derivatives. And instead of dt, we have dr. Then when we integrate this function and we evaluate it at point Q, our final point, minus our f evaluated at our initial point, hey, you know what? That's going to be the analogy to the fundamental theorem of calculus in the realm of multivariable world. Again, it's the gradient function, it's the gradient vector, because that contains the derivatives of the function that we're working with. And when we integrate, we take an antiderivative as part of that process. Okay, now that's our analogy. So we're going to kind of trust at this moment that this is what we call the fundamental theorem of calculus for line integrals. The only problem with applying this directly to line integrals is that notice that when we compute line integrals, we take some vector field, and we plot the corresponding vector in that vector field with the current change in position vector. So this is a dot product, and then what we're doing is we're adding up all of those dot products. So here, if I had a vector here, then my position would go, almost somewhat in the same direction. We do this in a different color. Here we're kind of going against the direction of the vector. Again, here we're kind of maybe a little bit perpendicular. And so when we're going to add these up, we're going to compute that. Now, this vector field, in general, is not necessarily a gradient vector. Well, this fundamental theorem of calculus for line integrals then will only work if our vector field is a gradient. In translation, we'll we will be able to more easily compute line integrals by evaluating endpoints whenever our vector field is a gradient field. Note that not all vector fields are gradient fields. Well, what does a gradient vector, what property does a gradient vector have? Well, we know that the gradient vector is specifically, it is a vector containing the partial derivatives of that function for which it is the gradient. So as long as these two are derivatives of f with respect to x, and the derivative of f with respect to y, then this will be the fundamental theorem of calculus for line integrals will in fact hold. Now, what consequence does this have? Before we get into any sort of calculation, so we're now going to state with confidence that if a vector field, again, any general vector field, is more specifically a gradient field, then it follows that that line integral is the same as again, this is just another notation for the line integral, but our vector field is a gradient field. Then the fundamental theorem of calculus for line integral says all we need to do is figure out what f is, evaluated at the point q, and evaluated at the point p, and then take the difference between those. This means that we need to know f of xy. Well, what was that function? And how do we know that this is the gradient vector? Well, somehow we need to go back and try to see if the integrals of these two functions will yield the same f. It will yield the same function. This brings to light something very important. The path to get from P to Q is not important if your vector field is a gradient field. Well, why is that true? Well, let's think about it this way. If these are two oriented curves, curve 1 is the one in green, curve 2 is the one in blue, then if the way in which we get from point P to point Q is independent, and as long as the vector field that we're seeing back here in the background, if this is a gradient field, then what we know is that the line integral for our vector field, which in this case is a gradient field, dr, along C1 is going to equal f of q minus f of p. Well, wait a minute. What about along curve 2? Well, along curve 2, that's still the vector field it's this gradient field that we're dealing with here, dotted with dr. Well, that is equal to f of q minus f of p. So this suggests that once I integrate, I just have to evaluate that integral at these two endpoints and take their difference. So since it only depends on q and only depends on p in this computation, these will be the same. These will be the same. Again, as long as our vector field is a gradient vector. So that's one of the beauties of this. So a path-independent field involves I should say, vector field that is a gradient field. Now, path independent, I'm going to loosely say that. We say that the line integral for a gradient field is path independent. In other words, the line integral between both paths is going to be the same, so the line integral is independent of which path you take, provided that the starting and ending point are the same for all of these different integrals. Okay. that means that these two line integrals are going to be identical. Well, let's go ahead and, before we jump into this, let's take a look at an example. Let's say that we consider the vector field given by f of x comma y equals, let's do x squared I plus y squared j. So in other words, our force vector at the position x comma y will be given by taking the x squared component, that'll be the x piece of our force vector, and y squared for the y component of our vector. So if we kind of imagine what this looks like, at the point 0, 0, our vector will be the 0 vector, so no movement at the origin. But if we look at the position, say 1, 0, 1 squared is 1, 0 squared is 0, so that vector will point to the right. Up here at the point, say 1, 1, this will be the vector 1, 1, so it'll point out that way. And then what we'll notice is that actually that same vector down here at 1, negative 1, since x and y both get squared, will be identical. So let's say that we pick two different paths. Maybe we want to go from the point 0, 0. We'll say p equals the point 0, 0, and we'll say that q equals the point 1, 1. And we want to think about the path that we take to get there. Now I'm going to argue that one such path is to take the straight line there. We'll call this C1. Now C1, the function that takes us there would be, for example, the function where y is equal to x. That line y equals x is that red line right there, or that's one variation of it. So as long as my x and y components are the same in my vector, my position, so we'll say my position as a function of time is going to be t. Now we could pick 2t, but the point is x and y are always the same along this position. And that just means that at time 0 will be at 0, 0. At time 1 will be at the point 1, 1. So if we were to compute the line integral, this would be our f evaluated at r of t, dotted with r prime of t, integrated with respect to t. So this will be, let's see here, so if we take this guy and replace x with t and y with t, we get t squared and t squared down here as well. Since this is the square of x, this is the square of y, x is equal to t, y is equal to t. Now we dot this with the derivative of the position vector. Well, the derivative of t is 1, and the derivative of the y component, which is also t, is 1. Integrate this with respect to t. Now, what's my time? Well, my time, it goes from 0 to 1, since that's how long it's going to take me along this position vector to get from the point 0, 0 to the point 1, 1. So if I evaluate this, I get the dot product between these is t squared plus t squared, which is 2t squared. The integral of that from 0 to 1 dt. The integral of this will be 2/3 t cubed, evaluated from t equals 0 to t equals 1. That's going to give me an evaluation of 2/3. So that is my line integral. That means that for the most part, since this is positive, we can actually see that this, based on just the limited number of vectors we've drawn, looks like that path is actually for the most part going with the current. So we get 2/3. Now, I'm arguing that this vector field is a gradient field, but we're not going to prove it quite yet. We're going to say there's another way to get from 0, 0 to 1, 1. And there's infinitely many ways to get from 0, 0 to 1, 1. But I'm going to say that another way to do that is parabolically. That the function y equals x squared will also take me from the point 0, 0 to the point 1, 1. So let me pick that position vector to look like this. I'll say r of t equals, and it just has to be the case that y is the square of x. So for x, I'll pick t, and then y just has to be the square of that, so t squared will suffice. You can pick anything for x. It can be 2t or even sine of t, as long as the y component is the square of the y, of the x, excuse me. Now, setting up this integral in the same way, in this case, at t equals 0, we see that we get 0, 0. So that'll put us at 0, 0 at time 0. At time 1, 1, 1 squared, well, that's going to put me at the point 1, 1. So integral from 0 to 1 again. F of r of t, so we're going to evaluate f at these two positions. So x is equal to t, so that means we'll have t squared. And now y is equal to t squared, so t squared squared is t to the fourth, times there, dotted with the derivative of the position vector. Well, the derivative of t is 1, the derivative of t squared is 2t, and integrate this with respect to t. Now, if this in fact is a gradient field, then this is a path-independent field, and I should still get 2/3. Well, let's see. So t squared, is the dot product there, plus 2t to the fifth, and we need to integrate that with respect to t. So this gives me 1/3 t cubed plus 2/6 t to the sixth. And I need to evaluate this from t equals 0 to t equals 1. Okay, so in this case, I get, well, let's see, 2/6 is actually 1/3. But if I plug in here, I'll have 1/3 times 1 plus 1/3 times 1. 1/3 plus 1/3 is 2/3. And then evaluating, putting in 0 here is just going to give me 0. So I'll have 2/3 minus 0 is 2/3, and here we see that these are the same. Now I'm going to make the argument that this guy is a gradient field. Now this doesn't prove it. Just because we get the same integral doesn't mean that it's path independent everywhere, but there is a way to address this now. So how do we know if a vector field is a gradient field? Well, let's think about a gradient field. A gradient field, we know, is the derivative, is a vector whose components are the derivatives of the same function with respect to different variables. Well, if I take the derivative with respect to y of the derivative of f with respect to x, I get a mixed partial. And the one thing that cool thing that we know about mixed partial is that if you get the same mixed partial if you take f of y and take its derivative with respect to x. So the two mixed partials we've learned, it doesn't matter whether you take the derivative with respect to x and then with respect to y, or you take the derivative with respect to y of that function and then take its derivative with respect to x, we get the same answer. So one way to tell if something is a gradient field is this will be a true statement. That if we take this first component, so let me just in general call this vector field f. We'll call this component here f1, and we'll call this component here f2. Because not every vector field is going to be a gradient field. These two functions may not be the derivative of some given function f. So if we take the derivative of f1 with respect to y, and that gives us the same as the derivative with respect to x of f2, then, I'll say if this is true, then f is a gradient field. So coming back up here to where we suspected that this guy, x squared y squared, remember back up here that in our example, that if in fact this is a gradient field, then what I should be able to do is to take this guy, which I'm calling f1, and this guy, which I'm calling f2. If I take the derivative with respect to y of f1, well, the derivative with respect to y of x squared is going to be 0, since we're holding x constant. If I take the derivative with respect to x of f2, well, we're taking the derivative of y squared with respect to x, that will be 0. And so we see that the two partial derivatives are the same, and so our conclusion, therefore, is that f is a gradient field. Excellent. Once we have that established, now we said that a path-independent field, let me back up here for a quick second, a gradient field will have this property that all you really need to know is the starting position and the ending position of your path, and that we, from the gradient field, can recover this function f, and then evaluate that function f at our two endpoints. This means that since our gradient vector contains the derivative with respect to x and the derivative with respect to y, notice that this is the derivative with respect to x of f. So if that's the case, then what I should be able to do is to integrate this guy with respect to x, and I should be able to integrate fy with respect to y, and I should get the same function, because they're derivatives of the same function just with respect to different variables. That means that if I can integrate the function, I can determine what that original function was, as long as I already know it's a gradient field. So for our example, we want to find f for our vector field, which was a gradient field, which was equal to x squared y squared. All right, so if this is in fact a gradient field, which we know it is, this x squared is already the derivative of some function with respect to x. This function right here is already some derivative with respect to y. So let's find out what f is. Well, f is going to equal the integral of f sub x with respect to x, right? Because this is already the derivative of that function. So now to figure out what that function was, we have to take the integral of it. So let me take the integral of x squared dx. Well, that's going to be 1/3 x cubed, and normally we would write plus c at this point. But let's think about, in partial derivatives, what kinds of things go away when you take derivatives with respect to x. So if I told you, for example, x cubed plus 3y squared, and I said find the derivative with respect to x of this guy, you know that the derivative of 3y squared, this would be 3x squared, the derivative of 3y squared would be 0. So that means whenever you're doing antiderivatives dx, you have to allow for the possibility that there might have been some function of y that got differentiated away, right? Like here, if we took the integral of 3x squared dx, we would say that it is x cubed plus some function of y that, when we took its derivative, may have become 0. Now, in our sense, we know that g of y is 3y squared, but here we have no way of knowing what that g of y is. So I'm just going to put g of y on the end. So you can see that by itself, taking the integral of f sub x is not adequate. we now also need to say that f will also be the integral of f sub y dy. Okay, now that means that the integral of y squared dy will equal, well, that'll be 1/3 y cubed. And like when we took a derivative with respect to x, when we take a derivative with respect to y to get y squared, any function of x may have been differentiated to produce 0. In other words, if you take the derivative of 1/3 y cubed plus h of x with respect to y, doesn't matter what this h of x is, its derivative will be 0. If you take the derivative of 1/3 x cubed plus g of y with respect to y, it doesn't matter what this g of y is or was, its derivative is 0. So what do we do now? We've got all these weird things floating around. Well, logically speaking, if f of xy, our function, is both equal to 1/3 x cubed plus g of y, and f of xy is also equal to 1/3 y cubed plus h of x, that means that these two functions have to be the same function. That means that these two have to be the same function, because one's the integral with respect to x, one's the integral with respect to y. Now, how could these possibly be the same function? Well, the only way for that to be true is if we say that 1/3 x cubed on this side, well, it can't be the same thing as 1/3 y cubed, but it is a function of x, so we'll say that 1/3 x cubed, let that be h of x. In a similar fashion, we'll say let g of y be 1/3 y cubed, and now we can say with great confidence that f of xy is equal to 1/3 y cubed plus 1/3 x cubed. And we can check our work, because if we find the gradient vector of this guy, let me just check my work, the gradient of this thing that I just found is the derivative with respect to x. Well, the derivative of 1/3 y cubed is 0. The derivative of 1/3 x cubed is 3 times 1/3, which is 1 x squared. And the derivative of this guy with respect to y will be 3 times 1/3 y squared, which is just 1 y squared. The derivative of 1/3 x cubed with respect to y is 0. And now notice that these two are the same. So we've used integration in kind of a new way to come up with what is this gradient function. Let's do a problem with this, and then we'll call it a wrap on this lesson. All right, so let's say that we have a particle that's subject to this vector field, yi plus xj, and this particle moves clockwise along the arc of the unit circle centered at the origin, begins at -1, 0, and ends at 0, 1. Find the work done by the force. Explain the sign of your answer. So let's go ahead and just give a rough sketch of this. We're starting at the point -1, 0, which is over here, which is -1, 0, and ending at 0, 1, and going clockwise along the arc of the unit circle. Okay. Centered at the origin. Find the work done by f. Well, first of all, I have to find a parameterization that will take me clockwise, and I know this is going to involve sine and cosine. So let me think about what's going to start my x component at a -1. At a -1, let me think about negative cosine of t. And for my y component, I'm going to think about sine of t. And the reason is that cosine, if I look at cosine, if this is t, cosine will start at 1 and go down to 0. but negative cosine will start at -1 and go up to 0, and then up to +1, and then down back to -1. So this is cosine like this, and negative cosine will take me from -1 to 0 in a matter of, this will be pi halves radians. Pi halves radians. Okay, so that means that in this case, this will go from -1 to 0, from t equals 0 to t equals pi halves. Let's make sure that sine of t does the same thing. Sine of t is going to start at 0, go up to 1, then down to 0, then down to -1, then back up to 0. So notice that at time 0, sine is 0. At time pi halves, sine is at 1. And so that's perfect. I want my y component to go from 0 to 1. I want my x component to go from -1 to 0. And so we're all set. We've got a parameterization from t equals 0 to t equals pi halves. So now to compute the vector field f evaluated at our position vector. Well, f, we know that this is going to be, the x component of the vector field is going to equal the y coordinate, and the y component of our vector is going to equal the x coordinate. So remember, this guy here is x of t, this guy here is y of t, and our position vector is going to involve y of t up here and x of t down here. No coefficients, it's just 1y, 1x. So there's 1y, 1x. So y is equal to sine of t, and x is equal to negative cosine of t. The derivative of our position vector, which we'll need, the derivative of negative cosine is positive sine, and the derivative of sine is going to be cosine of t. And I think that we're looking good. So now we need to compute this line integral. So this line integral will be the dot product between f of r of t, sine t, negative cosine of t, and sine of t, cosine of t, that's the derivative of our position, dt. It'll make it from here to here in pi halves units of time. So here we get sine squared of t minus cosine squared of t. And now we have to take the integral of this, 0 to pi halves dt. So we could use our technology to help us compute this. And interestingly enough, it comes out to 0. So that means that we're doing, at least from what we can deduce here, is that the amount of work that we're performing versus the amount of work that the vector field is performing, that those two fields cancel each other out. If we were to plot some of these vectors in here, let's see, we would have, would be positive, x would be negative. Yeah, so we get something that looks, vectors that kind of point down towards the origin, since the x component is going to equal the y value. The y values here are all positive, and the y component of our vector is going to equal the x value, the x coordinate, which are all negative, so they're going to point to the right and downwards. So basically in net, the amount of work done is 0, because the vector field did the same amount of work that the particle did traveling through it, so those cancel each other out. Now, is this a gradient vector? Is this vector field representative of a gradient vector? To answer part B, we just need to compute the mixed partial derivative, the derivative of this guy with respect to y, and that's equal to 1. And then we need to compute the y component, its derivative with respect to x, and see if we get the same thing. Well, we get 1, and so since the mixed partial derivatives are equal, we can say that f is a gradient field. Okay, so once again, what I did here is we said f is equal to the vector yx. This is what we're calling the f1 component and the f2 component. And if this guy here is already the derivative of some function with respect to x, and if this guy here is already the derivative of that same function with respect to y, then if I take the derivative of this guy with respect to y, that should equal the derivative of this guy with respect to x, if they're derivatives of the same function. And it looks like they are. So that means that this field is path independent, and there's infinitely many ways that I could get from the point -1, 0 to the point 0, 1, and it's not going to matter. I'm going to get the exact same line integral. Now, the path from here to here can be found in by parameterizing a line along the x and y axes that model this. So I'm going to say that this is going to have a slope of +1, increase of 1, increase of 1, and it's going to have a y-intercept of +1, so I'm going to argue that you could write the parameterization for the line y equals x plus 1. Again, many choices. I'm going to choose the simplest. I'm going to let my x component be t, and then my y component, I'm going to let that be x plus 1, which will be t plus 1. Now, I just have to figure out at what time is it at -1, 0, and at what time is it at 0, 1. So to do that, let me think about, I need this component to be -1. So if I let t equal -1, I'll get the point -1 and -1 plus 1. That'll be -1, 0. Our vector will be -1, 0. At t equals 0, our vector will be at 0, 1, as desired. So this is just another parameterization. And now if I evaluate the vector field at this position to calculate our line integral, well, that's going to amount to calculating the y component will go into the x position of our vector. The x component will go into the y position of our vector. And now I can compute my line integral from -1 to 0 of the position vector t plus 1, t, evaluated into our vector field, times the derivative of the position vector. The derivative of t is 1. The derivative of t plus 1 is 1. Integrate this with respect to t. Find the dot product. We get t plus 1 plus t is 2t plus 1. Integrate that from -1 to 0. And let's see, this is going to give me t squared plus t evaluated from t equals -1 to t equals 0. And this is going to give me, lo and behold, 0, which is the same value we got up here by using this arc parameterization. And the reason we're not too surprised is because this is a path-independent field. Now, here's kind of the clincher. The clincher is that if your vector field is a gradient field, then to calculate that line integral, all we have to do is calculate f of q minus f of p. So in this case, we started off at -1, 0. That's our p. We stopped at 0, 1. That's our q. And to get from this point to this point, we just need to know what f evaluated at 0, 1 is. I'll write it like this, f of 0, 1 minus f of negative 1, 0. So to find f, recall that we know now that the gradient of f is equal to, and by the way, this is producing the result of that fundamental theorem of line integrals, that this is equal to y and this is equal to x. So that means that this is already the derivative of our function f with respect to x, and this is already the derivative of that same function but with respect to y. So now step one, if I take the integral of f sub x dx, that is, this should give me the function f of xy, that is, take the integral of y with respect to x. Well, what's that going to give me? Well, that's going to give me y is a constant, so when you integrate a constant, you get the constant times x. Now, plus some arbitrary constant, but keep in mind that when you take the derivative of this guy with respect to x, any functions of y would have gone away. So to check our work, if I take the derivative of this with respect to x, the derivative of g of y is 0, regardless of what g of y is. Now, I also know that f of xy should be the integral of f sub y dy. That's this component. So that's the integral of x dy, and the integral of x dy, well, x is treated as a constant, so constant times y will be the integral of that term, plus what would normally be our arbitrary constant, which we'll just refer to as h of x. That its derivative would be 0 if you were to differentiate this integral with respect to y. And what do we know? Well, we know that these two functions have to be the same. Therefore, yx plus g of y has to be the same thing as xy plus h of x. And let's try to match things up here. So if I take, first of all, I notice that this is the same as this already. Now on the left I have a g of y. But I don't have any functions of y over on the right. So what do? Well, you know what? G of y could be 0. So we're just going to say that g of y is 0. And I'll come back and I'll write these in. And then notice that on the right I have an h of x, but on the left I don't have an h of x. Well, guess what? We're going to say that h of x is 0. Or some constant number, but for the sake of our problem, it just makes it simpler. Since we're doing a definite integral, we'll just say h of x is 0, and we'll say g of y is 0. That way, notice that the two sides are entirely equal to one another. In conclusion, f of xy is going to equal x times y. And our fundamental theorem of line integrals now tells us that all I have to do here is evaluate f at 0, 1. So f of 0, 1 will be this function with x equals 0, y equals 1, so 0 times 1, which is 0. Then evaluate that same function, the point negative 1, 0. So x is negative 1, y is 0, which comes out to 0. And check this out. This guy is equal to 0, minus this guy is equal to 0, and we get that that result is 0. So what did we save here? How did we benefit from this process? Well, up here we had to find parameterizations. We had to actually find an oriented curve that would take us from negative 1, 0 to the point 0, 1. And here we did it another way. It took us from negative 1, 0 to 0, 1 along that straight red line. But here we still calculated the line integral to be 0. We evaluated that line integral to be 0, but we didn't need to do any parameterization whatsoever. We just needed to compute a couple simple integrals discover what f of xy is based on matching things up from the two antiderivatives that we took, and then plug in a couple of numbers. So it actually was significantly easier. This is the beauty of path-independent fields. So takeaway from this is that if you have a vector field, and you can take the mixed partial derivatives of the two components and they're the same, then that means that you have a gradient field. And what that means is that it doesn't matter what path you take from one point to any other point up here. All we have to do is work backwards, take two integrals to find out what f is, evaluate f at this point and at this point and take their difference, and that result will give us the line integral regardless of what path we took.